Good morning. I'm Jeong from Jeong University. And actually, I'm one of the organizing members, so I'd like to say thanks for coming and doing work. So today I'm going to talk about quantum data hiding using Two-Qubit separable states. And this is a joint work with my postdoc, Dong, who is the next speaker of this session. And actually, this is based on a couple of papers, our recent papers about quantum data hiding. So it's not only about two-qubit states. Right, so this is the outline. First, we'll see some preliminary stuff about the concept of data hiding, both classical and quantum. Because the quantum data hiding we talk about here is based on quantum state discrimination. So we'll see some basics about quantum state discrimination as well. Then we'll move to the detailed scheme of quantum data hiding. And the scheme here uses the state discrimination of some special cases called quantum sequence discrimination. So we talk about quantum sequence ensemble and its sub-ensembles as well. Then we'll derive some sufficient conditions by which we can construct quantum data hiding scheme. And the condition derived here is only valid for infinite state, so we'll see some further improved conditions by which you can use some separable state to construct quantum data hiding. Then I'll summarize. Okay, for the concept of data hiding, let's think about the situation here. So there is a guy called Tiger here, and he wants to send some n-dimensional information I to both Alice and Bob. But instead of sending just I, say Alice and Bob, he just sends some information A to Alice and B to Bob. And here the A and B has some conditions here. Only just having A or B alone, they cannot obtain any information about I. So in other words, only having this A, the probability of guessing I is just random guessing. Okay? However, if they can collaborate, or in other words, if they can communicate, so if they have both A and B, then they can perfectly recover the information about I. Okay? So the term data hiding means here because the data I is hidden from each of A and B. Okay? However, every communication or operation here is classical, so it's kind of vulnerable to this group. So we want to do this quantumly to obtain some more security. So instead of sending just classical information I, we'll encode this bipartite quantum state A and B, row I, A and B, and either will send one part of this row in A, B to Alice and the other part to Bob. Okay? And for quantum data hiding, the condition is like this. If they just, even though they are allowed to classically communicate only by accessing their own particles, does not give any information about the prepared state. Okay? So the only way to distinguish this state is to perform some joint quantum operation. They need to quantumly collaborate. Okay? So even though we allow some this kind of classical communication, the data can still be reliably hidden from each other. Okay? So the thing we need to do is to find this kind of quantum state, set of quantum state, by which we can construct this quantum data. Because this is based on distinguishing which state is prepared, we talk about a little bit about quantum state discrimination. So because we are talking about bipartite quantum state, the bipartite theory is computed electricity, and then quantum state magnetically, and quantum state here is acting on this, there is a positive operator acting on this composite paper state with this mini trace, and any measurement is any set of positive operators having this complete discrimination. So the type of state discrimination is following. So there is a set of quantum states, and one of the states is prepared with some corresponding preparation probability. The test is yes, which state is prepared. Okay. And the system here, because the state is prepared probabilistically, we can think about the system as a probability ensemble of quantum state. So I use this concept, the state discrimination of an ensemble epsilon, that describes this situation. Yeah, so quantum mechanically, what we can do is to perform measurements to obtain some information about the prepared state. So we can use this kind of measurement operators, and the decision rule here is following. If M0 is detected, then we can just guess the prepared state is rho 0. Okay? No matter what the actual prepared state is. And as we know, the probability that rho I is prepared and Mj is detected is the inner product of these two operators. That's the premise in quantum mechanics. Yeah, because and if you think about the average success probability, this is nothing but the expectation of each success probability of these measurement operators. Of course, this is the case when this ensemble is prepared, and if we use this set of measurements. And because this expectation of success probability is always between 0 and 1, and we also know that the perfect discrimination is possible, and it can only, all of these states are orthogonal, mutually orthogonal to each other. So that's the equivalence condition. And if you think about the maximum average success probability of all possible measurements, and it's denoted by PG, which is for guessing probability. Here G means, G is from guessing, but it also means that there is no restriction about the set of measurement. We can use any measurement to distinguish this, or to discriminate which state is prepared. Yeah, because we are talking about bipartite quantum state discrimination, we can think about some constraints on the set of measurement. If only LHC measurement were allowed, that means LHC measurement means measurements performed only by local quantum operations and classical communication. Okay? And we can also think about maximum average success probability of all possible LHC measurements. Okay? Then we denote that as PL. Then clearly we can see that the set of all LHC measurements is a subset of all possible measurement here. We can always have a trivial inequality. This PG is always larger than 1 equal to PL. And for the case when this PL is strictly less than PG, then in that case we say that there is some non-locality in this state discrimination. So again, by using the language of quantum state discrimination, quantum data hiding can also be phrased like this. For this given ensemble, so rho I, AB will be shared to Alice and Mark. And to perform this quantum data hiding, this ensemble needs to satisfy some conditions there. By any analysis measurement, the probability of discriminating this state is no better than just random guessing. This is one of the stuff. However, if they can perform some joint measurement or joint quantum operation, then they need to be orthogonal to each other so that this PG is 1. Okay? By using joint operation, they can perfectly recover the information about this state, and only by LHC operation, they can do anything. They cannot obtain anything, any information about the state. Okay. So besides this kind of application of quantum data hiding, actually data hiding can also give us some good insights about some fundamental concept of quantum information theory, which is called boundary entanglement. Okay, so briefly speaking, boundary entanglement is a special type of entanglement which cannot be distilled into any pure entanglement by means of local operations and classical communications. So, okay, so let's think about this kind of four-party state. So rho AB, A prime, B prime. And the first two parties are in the state of these two base states. the P plus or P minus. And on the other two party, these base states are labeled by this row 0 and row 1. Okay? And if this row 0 and row 1, this ensemble can be satisfies the condition of quantum data hiding. That means it cannot be distinguished then by error estimation, but it can perfectly discriminate it by global measurement. The task here to do is to distill some free entanglement on this part. So we can't really touch anything about this part A, B. The only thing we can do is to discriminate the label between the states, row 0 or row 1. But as we have seen before, by using some global measurement or global operation, we can perfectly discriminate row 0 or row 1. That means we can determine the state in the system AB is either P plus or P minus. But only by error system measurement, because we can't really distinguish anything about these two. So the state of the system AB is nothing but a mixture of this P plus and P minus, which is always a separable state. Okay? So by using this concept of quantum data hiding, we can see some structure of bounding entanglement states. So to do quantum data hiding, we need to find some state ensembles satisfying both of these conditions. Okay? However, if we think of a little bit carefully, so it's like this. To obtain that this PL is just random guessing, so and then the probability here needs to be uniform. Otherwise, we can always guess the state with the largest probability, which is always larger than this uniform probability. So this probability here is uniform, and moreover, if there is any distinction between some of these states, then we can always use that distinction to perform discrimination better than random guessing. So it can be true. So to obtain this here as just random guessing, so we can see that the probability here is uniform, and every state here is identical to each other. In that case, trivially this PG is also just random guessing. Okay? Because we are dealing with identical state with uniform probability. So what we have seen here is that for any quantum state ensemble, it cannot satisfy both of these conditions. Okay? So just by using this one-shot implementation, we can't really do any quantum data hiding by using any quantum state ensemble. So what we want to do here is to use this ensemble several times. Okay? We don't use all quantum state ensemble, so that this PG is always 1. But here. So by using this ensemble several times, we could find some condition that this PL tends to random guessing asymptotically. So because we are using this several times, the thing is like this. So in the first round, maybe this row B1 is prepared with this corresponding probability. On the second round, row B2, and so forth. Okay, so after say capital L round of this stage, the state of this system will be the tensor product of each state prepared in each round. Okay? And also this preparation is independent from each other. So the probability of preparing this state is nothing but the product of each probabilities at each round. Okay? By the way, if you have any question, please interrupt me.
I will have one question.
Sure.
Can you go one slide previous, and then you have the still one where, well, actually also this one. So you're saying that there is no example satisfying the strict conditions. Is it known how close to uniform distribution you can get in this single round scenario? Like how much, if we would like to have an example that I would put together can discriminate how much information they must have.
if you ask me some general answer, I don't know. But what we have done here is we could find some condition by which we can approximate this one to random guessing.
Okay.
Yeah. So, and actually it's not discriminating the it's not just discriminating the sequence here. It's discriminating some properties of the sequence.
Okay.
Yeah.
Yeah.
There's no caption. So because this is a sequence of quantum states, so the index will be, this vector will be used as the index of this sequence. So that means that on the first round, the row V1 is prepared. On the second round, row V2 is prepared, and so on. Okay. So I use this notation, epsilon penta F, that represents the ensemble of these quantum sequences, together with these corresponding probabilities. And one more thing we can define here is the weight of this index vector. Okay? Because this vector is in Zn to the R, we can think about the summation of all the entries of this vector in mod n addition. Okay? Then it's always in this Zn. That means it's always between 0 and n-1. Okay? So for this given quantum sequence ensemble, if the state the sequence row B is prepared, what we are interested in here is to guess the weight of this index vector, not discrimination of this prepared state. That's what we want to do. So it can be thought like this. From this quantum sequence ensemble, this ensemble can be decomposed or partitioned into the set. In this set, every state here has the same weight of the index. Okay? We can partition this ensemble of quantum sequence into subsets in which every state has the same weight of the index. And because this is not a probability ensemble, we can further normalize this. Okay? So this one, so we can just add all the probabilities in this subset and divide this by this summation, so that this one becomes a quantum state ensemble. Then this quantum sequence ensemble can be thought as the weighted union of this sub-ensemble. And then we can think about the preparation of this quantum sequence like this. In the first place, this sub-ensemble is prepared from this quantum sequence ensemble. Then in this sub-ensemble, the state row B is prepared with, together with this corresponding probabilities. Okay? Then guessing this weight of this index of this sequence is equivalent to say that guessing which sub-ensemble is prepared, not discrimination of this quantum sequence itself. And also we can think like this. For this sub-ensemble, because the probability ensemble is nothing but the mixture of the all state with these probabilities. So we can think about we can make the correspondence between this sub-ensemble and these states. Let's say row I to the parentheses. That means the mixture of all the states in the sub-ensemble. Sub-ensemble here, and the normalization. Okay, then the discrimination of the weight of this index here is equivalent to say that the state discrimination of this ensemble of mixtures. Right. So this is the summary. So for this given quantum sequence ensemble, we can think about the another quantum state ensemble, which consists of the mixture of the state with the same weight of the index. Then guessing the weight of this index for given quantum sequence is equivalent to discriminate this mixture of the states in this ensemble. So everybody's okay with this. Right. So then we're going to use the task of guessing the weight of this index to construct quantum data hiding. It's like this. If we can find some condition that PG of this epsilon parenthesis L is 1, in other words, by using joint operation, the index of the vector will be perfectly discriminated. However, if we just use LOCC measurement, then the task of guessing, the probability of guessing the index of the weight tends to just random guess asymptotically as L increases. Okay, here we can also note that if every state here is mutually orthogonal to each other, then everything is orthogonal. So this PG of epsilon L is also 1. That means the state in this mixture are orthogonal to each other as well. So the scheme of quantum data hiding is like this. So in the first place, the hider will prepare the state from this state ensemble and share this L above, and he repeats this capital L times. Okay?
Yes, so we're comparing PG and PL.
Yep.
So for whether we get PL is allowed to is a local classical communication between ends and values.
Yeah, it's on
Allow for each sequence.
Yeah, for each sequence, classical communication is so each classical communication is allowed, and moreover, it's also possible that Alice maybe can store all of her states. Then she can also do collective measure as well. But that's the case when they have quantum memory. Otherwise, they just perform measurement immediately right after they receive this each round, in each round. Okay? So in that case, there are some more restriction on the measurement that they can perform. Alright, so if you assume they have quantum memory, the state after this L round is nothing but the quantum sequence that we have talked about. And the second step is like this. The hider wants hide this classical information X between Alice and Bob. Then to hide X, he just evaluates the weight of this quantum sequence he prepared. And then he will just add this to X and Y in mode M. And then he just announces Z to Alice and Bob. Okay? Once Alice and Bob know Z, and to recover this X, they need to know this Y, which is the weight of the index of the quantum sequence. Because we're going to use orthogonal state ensemble, PG epsilon is always 1. That implies that PG of this epsilon is also 1. So one sufficient condition we can find here is that whether we can approximate this PL of epsilon n to just random guessing as n increases. So to bound this PL. So to randomize this PL, we want to use some upper bound of this PL, and that's so-called PPP, which is the maximum of average success probability, and the maximum is taken over all possible PPT measurement. Here, PPT measurement means that measurement in which every measurement operator is still positive on the partial transformation. The one thing known here is that every analysis measurement is PPT measurement. So PPT set of all PPT measurement is a larger set than the set of all analysis measurement. So we have this trivial inequality, and also set of all PPT measurement is included in set of all general measurement. We also have this inequality. So this one plays an upper bound for this PL. Okay? And as mentioned before, so for this given quantum state ensemble, we can just guess the state with largest probability. So which can be trivially done just by analysis. Maybe they can just do. They don't really do anything, but just guess the state with large probability. So the maximum of these probabilities is always a lower bound of PL, which is always bounded below by this mean of these probabilities. So we have all of these kind of trivial inequalities. So the strategy here is to randomize this one. Actually, the upper bound of this one. So that everything can really be the same. And yeah, so it's an upper bound of PPP, which we have defined before. It's called QG, which is maximum of all possible measurement. And the term we're going to maximize is the expectation of this inner product of this measurement operate and the partial transpose of this state in this answer. Okay. Then one thing we can easily show is that this one is always an upper bound of this PPP. Okay. So it's because it can be easily seen because in the trace, this the trace is invariant on the partial trace position. So if you think about the partial trace position of it, then this one becomes the trace of rho I times n PPP. So n to partial trace position of n I. So if you think about PPP measurement, it's still measurement on the partial trace position. So this maximum covers all possible PPP measurement as well. Okay, so this one is trivially, we can easily say this one's the upper bound of this PPP. So we have this inequality, and what we want to do here is to randomize this one to randomness. Okay. So one result we obtained here is that for any state ensemble epsilon, and for any quantitative integer L, the QG of epsilon L is always bounded above by this term. So because if we see the term inside this L, if this one is strictly less than 1, then this one will decay to 0, exponentially with respect to the number of iterations. Okay? So by vanishing this one to 0, we can make everything here to be same to each other. Okay. So it's a sufficient condition. If QG of epsilon is less than 2 over m, then we can see that the limit of this PL of epsilon to the L is it tends to random guess 1 over epsilon. 1 over m. And this is an example of quantum state satisfying that condition. Okay, so it's like this. For any empty state, we can think about these two states, rho 0 and rho 1, like this, with some corresponding probabilities. Then we can easily say these two are orthogonal to each other, and moreover, that QG of this epsilon is less than 1, which is the case of 2 over n when n is 2. Okay? So it satisfies the condition of quantum data hiding. So by using this two-state ensemble, we can construct a quantum data hiding. We can also think about more numbers of quantum states, more number of information to hide. So so for any n which is a power of 2, we can think about this symmetric and anti-symmetric Bernoulli state in two-qubit system. And by using this, we can construct these states, rho I, okay, which is 2 to the n number of states. And then together with these probabilities, we can show that this one satisfies the conditions of quantum data. So we can use this one to hide any n-dimensional classical information. That's the case when n is 2 to the n. But we could also show that by using some of these states, we can also construct quantum data hiding. So that means we can construct quantum data hiding scheme for any number of them. So this is some examples that the case. This is the case when n is 2 and n is 3 and n is 3, n is 6, and n is 9. And this is the number of iterations. And this is the value, the upper bound of the value of PL. So just by iterating several times, or 4 or 5 times, HPL tends to random guessing rapidly. Okay? So we don't need to use many rounds to randomize this PL. Okay, so let's move to separable state and data hiding. So any questions so far? So all comments? Right, so what we have done here is to randomize PA by using the upper bound of PA, which is PG. But if you think about this PG, we can see one fact there. If any orthogonal PPP state ensemble, that means every state here is state positive on the partial transposition, then we can easily see that this QG is always 1. Okay? The thing that we have done before is by randomizing this one to randomize this PA. But for any PPP state ensemble, this one is always 1. So we can really use this upper bound to randomize PA. So in other words, by using this upper bound to randomize PL, this ensemble contains at least one intangible state. Okay? So maybe we can think like this: whether or not this entanglement is necessary for quantum data hiding, or is there any separable state ensemble to construct quantum data hiding scheme? And yeah, so for separable state to construct quantum data hiding, we could find some new bound for PPP. So it's like this. So from now on, we just talk about two-state ensemble. That means we're going to hide one bit information. And for any two-state ensemble, say rho 0 and rho 1, we will define this lambda of epsilon as the weighted difference of these two. Then one thing that we can show is that if this lambda epsilon can be decomposed into some Hermitian operator and this partial transposition, then we can show that this PPT is always bounded above by half plus the trace norm of this H. And one thing we can note here is that if this lambda epsilon is invariant on the partial transposition, then yeah, this one is equal to this because we can use this half of this as H. However, we also note that this kind of H is not unique in general. There can be, so if this one is false, then there can be several H's satisfying this decomposition. And for each H, we can obtain an upper bound of this PPP. And moreover, if we think about the minimum of all possible such H that can decompose this lambda epsilon, then the minimum will give the exact value of PPP. Again, yeah, this is another optimization problem, but this PPP can be rephrased in terms of this trace norm of H that can decompose this lambda epsilon. And yeah, so new bound for PPP is like this. For this two-state ensemble, satisfying this invariance of this lambda epsilon under partial transposition. And for any, if there is some positive integer k and Hermitian operator A satisfying these conditions, that and this one can be decomposed into this, and the product of this trace norm of H and its partial transposition multiplied by 4 is always less than 1. Then we could show that this PPT of epsilon L is bounded above by these values. As you can see, because this one is less than 1, that means this one decays to 0 rapidly, I mean, exponentially with respect to the number of iterations. And as a corollary of this, we could also obtain this result. So for this two-state ensemble, if it satisfies this condition, then we can also bound this PPT of epsilon L in terms of these quantities. So this is a corollary of the theorem, but so I have two references here. It's because actually we obtained this corollary as the main result of the first paper here. And so we could find some separable state ensemble by using this one to construct quantum data hiding scheme. But the examples that we could find is having dimension larger than or equal to 3. So we couldn't really find any two-qubit state ensemble for which we can use this guide to construct quantum data hiding scheme. So, and also, it's like this. So this is kind of arithmetic mean of these two, right? But the new bound here is actually the square of the geometric mean of these two. So that means if this one is, so it's like this. So if this one is satisfied, that means this one is always satisfied. Okay? But the other way is not always true. So this theorem means that, it's like the corollary is satisfied, then theorem is always satisfied. Okay? But the other way is not true. So we could find some weaker condition for which we can construct quantum data hiding by using two-qubit separable state ensemble. Right. So this is the example of two-qubit state ensemble, which can be used to construct. Yeah.
So H is a weakness in practice.
So weakness in what? H plus, actually H plus this HPP is weakness.
Is a weakness.
Yeah. So it's in the dual set of PPT operators. Yeah. So it's decomposable. Then, so if it's not positive, then we also call it this is a decomposable weakness. Because we are talking about the upper bound of PPT. So we need to think about one way to obtain this to think about the dual set of PPT operators.
So H itself is Heston operator. Eta 0, rho 0 minus eta 1, rho 1 is H, isn't it? Please recall that.
So yeah, it's like this. If this eta 0, so if this is the invariant on the PPT, then we can use just half of this as H. So that's what you are saying.
Yeah.
But it's not unique. So that's not the only one, usually. There could be some other H satisfying this decomposition.
Yeah, thanks.
Okay. So, right, so by using the theorem, you could find this two-qubit state ensemble, which can be used for quantum data hiding. And the construction is quite straightforward. This is trivially separable state, and this plus beta and minus beta is invariant under transposition. So we can easily say this one is satisfied. It's a bit complicated. So by using this 2x and 2-qubit orthogonal basis, we can think about this 4x4 orthogonal basis. There are there are 16 number of basis elements here. And the reason why we have constructed this is to think about so for this 2-qubit state ensemble, we can think about this lambda epsilon and think about and think about tensor product of this. Okay, so this is the case when k is 2. Then it can be re-weakened in terms of these orthogonal bases. And moreover, we can also decompose this into H plus HPP, where H can be written in this form, and its partial transposition can be evaluated like this. Everything here can be described in terms of this orthogonal basis and provide the quantum system. It's a previous speculation, but yeah, it's true. And then, if we think about this trace norm over H and the trace norm over HPP, it can be described as a function of theta, say at 0 and at 1 of theta. And the condition that, the condition that the product of these two together with this 4 is less than 1, then becomes that, becomes this. Because this one is this, and this F1 of beta is this. Okay? So all we need to do is find some variation of beta satisfying this inequality. Then we could efficiently bound this PPT by this. I mean, we can efficiently vanish this one exponentially as n increases. And this is the graph of 4 times f0 and f1. And we could find some interval here between theta between pi over 6 and pi over 4. It's always strictly less than 1. Okay, for those theta, we can use those two state ensembles to construct two state quantum data in this case. Okay, so this is the case when B is larger than 3. This is the previous result. Actually, we could find some quantum state ensemble satisfying the corollary, which is a stronger version. Okay, so by using this, we could find any. We could construct quantum state, quantum data height to hide one bit information. This is the derivation. So maybe you can look up the paper for the detail. So I guess that's it. So to summarize, so we have constructed quantum data using various quantum states, and the latest result is that 2-qubit orthogonal separable state can be used to construct quantum data hiding. That means we don't really need entanglement for quantum data hiding, and we can also use the quantum state with the lowest dimension to construct the quantum data hiding. And this was done by exploring some sufficient conditions for quantum data hiding. And possible future work we can think about here is that because we have only talked about bipartite quantum state, so maybe you can think about some multi-part quantum states to hide data for many people larger than 2 people. And another thing is that so the reason why we could construct this quantum data hiding scheme is to use the non-locality in quantum state discrimination. And we could find some sufficient conditions quantum data hiding is possible. Then one natural question we can give here is that whether or not this local indistinguishability, I mean the non-locality in quantum state discrimination is always sufficient for quantum data hiding. So that would be another interesting question we can think about. So I guess that's it. Thanks for your attention.
Thank you for the master. Any question from audience?
Yeah, it was a very interesting talk. Thank you. I was wondering, can you give some sort of scenario where this is relevant? Because so what you're doing is you have this idea of quantum data hiding. So you hide data against some adversary that is restricted to LOCC. But how would you enforce this? I mean, how can you be sure that your adversary is restricted to LOCC, or when is this relevant?
Yeah. That's a good question. Actually, this is not something like sharing secure information. So I just want to make them, they don't have any ability to access to the data individually. So it can be reliably hidden from, let's say, the number of people here. That's what I want to do. So it's like I don't want to give the whole information to all of you.
Yeah.
I just want to share some information, but it's not just sharing. Just by individual observation, they need to have no information. They need to have no correlation with the actual data. Once they get together and do collaboration, and they can obtain the hard information.
Yeah.
So that could be some kind of, it's another task, it's another task, like secure communication. So, is it enough to your question? Or? So of course, we can't really impose them not to collaborate.
Yeah, exactly.
Yeah, but
Behind your back, we
Yeah,
could,
this
you
is
share
another-
information with us, and behind your back, we can just gather in one separate room
Yeah.
and then crack the secret.
Mhm.
Well, but perhaps there is this gives, I mean, also the classical, I don't know, there is this thing that if I send you something and now I send Anu something in US clock, then I can take time and knowing that secret is
Mhm.
for a certain time that it takes for you to travel to Finland. So I can kind of estimate the time, how long the secret is. But I agree with you, of course, in the eventually.
Yeah. May I ask another question? Are there similar considerations where you clearly distinguish, so you have the same concept of data hiding, but now you clearly distinguish between local parties only being restricted to classical resources versus parties that have the availability of quantum resources? I mean, because if it's classical, then we don't need to worry about LOCC separateness, because it's the same. But is there maybe a gap? So can we make the data somehow harder to access if one is restricted to classical operations versus quantum? Maybe some in the literature.
Difficult question, because you want to make some distinction between quantum and classical. So
Yeah.
it would be, yeah.
That's what I
more
like to do.
difficult. I don't really have any idea. That's
Okay.
a question at this moment. And, yeah, I think about this.
Okay, thanks.
We can talk about this later.
Sure.
Okay.
So in this data hiding scheme, okay, with perfect like uniform probability for like locally and globally with probability 1, could you also think about relaxing? Now you relax like the uniform probability for local, could you also think about relaxing the like keeping strictly the uniform probabilities but relaxing the like unit probability for the global or some kind of like the limit approaches?
Yeah, that's also a good question. So, but as we have seen here, if the LOCC discrimination is minimum, then the global discrimination is also so it's random guessing. The LOCC discrimination is random guessing, and the global discrimination is also random guessing. So maybe you can think about both bounds at the same time. But there are some skills to construct quantum data hiding in that way. But this one is more efficient because once we have this bound, we just need to randomize the answer.
Yeah.
Okay, if we consider the situation that there is entanglement, so they can use LOC-specific entanglement, then what can we say?
Once they have entanglement, they are not no more restricted to LOCC because they can use entanglement to do some quantum collaboration. So in that case, the boundary will be higher. So
Is it possible to
so it depends on how sorry.
in the case, is it possible to?
So maybe we can obtain some bound, but it depends on how much entanglement they share. It depends on the amount of entanglement. And due to the amount of entanglement, maybe we can find some bound. But it's just intuitively. But I think it's
Yeah, this, I mean, very nice result about the limit, and it goes to infinity and then another. But can you say something about how fast is the
Yeah, as I mentioned, it's exponentially fast.
Okay.
2 tower speed. Because the bound we found here is something like this. So we want to randomize this one. The upper bound here is on this one. So the term inside here is less than 1. And here L is the number of iterations.
Oh, yes.
Yeah.
Okay, okay, thank you.
It is pretty efficient, I guess.
Okay, any other question? Okay, then let's thanks, Victor again.